That's good.
Okay. What I want to talk to you today about is extending Pythagoras. There's certain minimums that you assume when you lecture in large places. I will assume everyone has seen the Pythagorean formula before, or if not, can fake it. Hopefully one of those two is fine. Alright, so the goal of the talk is, often we say, I want to give you a proof of something. We say a proof and not the proof, because there's many different ways of looking at results, many different paths you can take. I want to talk a little bit about what you can get by choosing one path rather than another. So different proofs highlight different aspects. Too often, one way of proving things is by doing a lot of tedious, unenlightening algebra, and at the end, the answer pops up. Well, this is good and gives you the result to use. It doesn't always lead to understanding. And so I want to talk about some other ways of looking at connections between objects that hopefully you've seen before, and how you can then use that to attack new problems. So in particular, the specific result today is the Pythagorean Theorem. Alright, so I'm going to assume everyone has known it, but just in case, you have a right triangle the sides of A, B, and C. We can talk later as to which one should be A and which one should be B, but they sandwich the right angle. And so if you have such a triangle, then A squared plus B squared equals C squared. I'm assuming everybody here has seen this. I'm curious, how many people, if all of a sudden I have to go pick up my kids, which has happened when I've talked to you before, how many of you could prove the Pythagorean Theorem right now? We definitely should have challenged geosciences to proving the Pythagorean Theorem. Alright, so let's talk a little bit about proofs. So here's one of the famous proofs, Euclid's 47 proposition, book 1. One of the big things you will see in geometric proofs is drawing auxiliary lines. Always the question is where. If this is not too illuminating to you, I've now put it in color. So hopefully this is now all clear. And here is a proof of the Pythagorean Theorem. I will let you digest that a little bit later. Alright, how about this one? Convinced or not convinced? If you go through and carefully measure all of these, I've never done this and I've never had a student I've been so upset with that I've assigned it, you should probably be able to see that all the regions do correspond as stated, and then this will be a proof of the Pythagorean Theorem. However, this is extremely unenlightened. Why are we dividing up the region like this? Why do we have this kind of correspondence? This is the first proof of the Pythagorean Theorem that I can actually remember seeing. You always, the first proof of Pythagoras is always special to mathematicians. So I got this in a physics class. So you have a triangle, AB. It's a right triangle. The area of the triangle is 1/2 the area of the corresponding rectangle. So I'm going to assume we have these basic knowledges. The area of a rectangle is just length times width. And so I have 4 small triangles. Each of them has area 1/2 AB. So the area of the 4 triangles is 2AB. The area of the big square in the center is C squared. And I'm going to do one of the things we do all the time in mathematics. I'm going to count what I want 2 different ways. So the area of the big triangle is the big square is A plus B squared. And I can also write it as 4 of the triangles plus the square in the middle. And so if we equate them, we get A squared plus 2AB plus B squared is C squared plus 2AB. We can safely divide, safely cancel, dividing is hard, we'll talk about that later. We can safely cancel the 2ABs and we get A squared plus B squared is C squared. Here's another way of doing the 4 triangle proof. And you can see now I'm just rotating how things are, and I'm putting the triangles in different ways. The 2 regions must match, and so since they must match, it's another proof that A squared plus B squared equals C squared. This is Williams. When you talk about Pythagoras at Williams, you have to mention James Garfield. Not only was he a US president, but he is also credited with a proof of the Pythagorean Theorem. And so this is his proof, which is completely different than drawing a line diagonally here. But he is credited with a trapezoidal proof of Pythagorean Theorem. So again, if you remember your trapezoid relations from high school, you can go back and fill in the details of this. In poli-sci, later in the fall, I will talk about how this did lead to his presidency. So there's lots of difficult proofs that we can do. The goal is not to do difficult proofs. The goal is to do enlightening proofs, proof that will help you get a sense of why things are true. So I want to talk about dimensional analysis. So for the physicists here, for the chemists here, you hopefully do stuff like this, factor labeling all the time, keeping track of units. We don't do this nearly enough in my mind in mathematics, is you're keeping track of what things are. So here are 5 possible candidates for the Pythagorean Theorem for relations between A, B, and C. Now we know, of course, that all of these are wrong, hopefully. Can anybody tell me a reason why any one of these might be wrong? Yes.
If you cube a side, you're talking about volume. So
Good. So the first one is basically saying an area is related to volumes. Probably not right. What about the second?
not symmetric.
It's not symmetric. You know, I shouldn't be able to see differences between A and B. So 2 looks a little fishy. What about 3?
Not symmetric.
3 is not symmetric, but even worse than not symmetric. Yeah, B is larger than A. You have some serious issues there. What about 4? What about 4? Yeah, I can't think of any reason against 4 either. 4 does seem like a natural candidate. What about 5? Any reason why we should eliminate 5 from consideration?
Where 1 through 10?
I gave a talk at the 110th anniversary of a Mathematical Teachers Association, and I discussed this there, so that's where the 110 came from. Usually, though, it's something related to Star Trek or my kids with me. So there is a reason why the 5th one should be eliminated. A squared plus 2ab plus b squared is a plus b squared. And if you have a triangle, the sum of 2 sides should be greater than the third. And so if this were the case, then c would be greater than a plus b. There should be no way to close off the triangle. So here, only the 4th one is still possible. Now, of course, you know, it turns out that there is no AB term at all, but it's at least possible. So what I want to do is I want to do a dimensional analysis proof of Pythagoras. So area, I claim, is a function of the hypotenuse c and the angle x. And if you want, if you think of trig, if I know the hypotenuse and the angle, I know b is c times cosine x, I know a is c times sine of x, and the area is going to be 1/2 c squared sine x cosine x. At this point, I've forgotten trigonometry, so I do not know the actual relationship, but there should be some relationship. Once I specify the hypotenuse and the angle, the rest of the triangle is uniquely determined, the area follows. So the area is some function of the hypotenuse and the angle. I'm going to write the area c of x, c comma x, as some function of x times c squared. And the reason is, if I keep the angle fixed, and if I triple the hypotenuse, well, if I triple the hypotenuse, I triple A, I triple B, by similar triangles, and so the area increases by a factor of 9. So I don't know exactly what the formula is for the area as a function of c and x, but I know a little bit about its functional dependence. It's got to be some function of x times c squared. Determining exactly what that function f of x is would be too much of a digression, so I'm not going to go into the depth of that, but I know this relationship with c squared. All right, so almost all good geometry proofs have you drawing an auxiliary line somewhere. The first one I showed you had a lot of auxiliary lines. The second one with 5, 6 different regions had even more. We can do this with drawing just one auxiliary line. What we're trying to do is we're trying to deal with right triangles. So how can I draw an extra line and get more right triangles? Well, I can draw a line from the corner up to the hypotenuse C. And that's going to give me 2 more right triangles. And if you use corresponding parts of congruent triangles or congruent, if I remember the acronym correctly from high school, you get that that angle there is the same angle as that angle there. So the 2 triangles, actually all 3 triangles, they all have a right angle, and they all have a smaller angle of the same measure x. We have now almost proved Pythagoras. And the reason is it's going to go back to something we've seen earlier. We're going to count something 2 different ways. I'm going to count the area of the big right triangle as the sum of the areas of these 2 beautifully labeled triangles 1 and 2. Can somebody tell me what the area of triangle 1 is? So what's the area of triangle 1? Yes? F of x a squared. We know that the area is, of a triangle with angle x, is equal to f of x times the hypotenuse squared. So we get f of x a squared plus f of x b squared equals f of x c squared. I was originally going to then just go and immediately say a squared plus b squared equals c squared, but after the warnings about lab safety, you've got to be very careful. Okay? So please do not immediately jump to here. Make sure f of x is not 0 before you divide by it, otherwise bad things can happen. So I will leave it as an exercise to prove that f of x is not 0, okay, and that it is safe to do the division. Here's Pythagoras. It's fundamentally a statement about how areas combine. As an example from physics, this was for Tiku, who's not here, but he's looking at other balls right now. I should have really changed the image. I want to figure out what is the period of a pendulum bob swinging. What quantities do I have at my disposal? I have length, acceleration, mass, period, and angle. I have the different units for them. I'm not going to go into too much detail, but I need a combination of these quantities that get seconds. And when you look at it, the only combination that works is the square root of L over G times some function of the angle. And without doing any experiments, I can predict the functional form of the period should be related to the square root of the length over the gravitational constant G. So what I want to do now is I want to try to guess the Pythagorean formula. So I'm going to pretend I don't know it yet, and I'm going to see how we might guess it, and then I'm going to extend this to hopefully a place where you have not seen the Pythagorean formula. So the idea is we want to guess the correct function. I'm going to have some free parameters, and I'm going to try to nail down those parameters by looking at some special cases. Natural guess, linear, quadratic. Why are these natural guesses to make? Why would I guess linear or quadratic? They're simple, right? Try the simple cases first. Hope that you get a simple relation between the various things you want. If it doesn't work, complicate the model, add more bells and whistles. All right, so let's guess a linear relation. So let's guess the hypotenuse is some number times A plus some number times B. And we want to figure out what those numbers alpha and beta are. So we're going to consider special cases. So I imagine a very long, thin triangle. I'm deliberately not labeling the sides A and B so I can do it both ways. As the triangle gets very, very long and very, very thin, so say A is going to 0. Well, if A is going to 0, the length of the hypotenuse is almost the length of B. So as A goes to 0, B has to be going to C. The only way that can happen is if beta equals 1. Similarly, if I go the other way around, I get A has to go to C, and thus alpha has to be 1. So the only possible linear relationship, if the Pythagorean theorem is linear, is C equals A plus B. And so does this make sense? Well, if it's linear, it's got to be A plus B. I've said before, the area of a rectangle that's x by y is xy. If it's a right triangle, it's 1/2 xy. So hopefully this is visible. Is the square visible? Okay. So let's imagine A equals 1, B equals 1, and C would equal 2. I've got 4 right triangles. I put them all together and I make a square. And now, because I have a square, the sides of the square are 2, and I have 4 triangles that have sides of 1. So I can calculate the area of the big square 2 ways. The 4 triangles gives me a total area of 2. The big square gives me a total area of 4. 4 does not equal 2. Therefore, the Pythagorean formula is not linear. Right, so by looking at one special case, this was enough to disprove that it could be a linear relation. Let's guess a quadratic. So let's guess it's alpha A squared plus gamma AB plus beta B squared. What are alpha, beta, and gamma? Can anybody tell me one of the quantities alpha, beta, or gamma? Do we know any of them? Yes?
Alpha and beta should be 1 by the same argument.
By the same argument as before. This is what we do all the time as mathematicians. By a previous case, reducing it to something we've already done, alpha and beta have to be 1. It's the exact same argument as before. Consider the very, very thin triangle with one going to 0 and the other going to infinity. So the difficulty is, what is gamma? Well, I'm lazy. I could do this with the 30, 60, 90 triangle. I will do it with the same one before. The only difference is now instead of a 2, I have a c. And so now if we equate areas, I get c squared has to be 4 times 1/2. So we get c squared equals 2, or c equals the square root of 2. So if we substitute 2 equals 1 plus gamma, 1 times 1 plus 1. So gamma has to be 0. So we get c squared equals a squared plus b squared. The Pythagorean formula. This is not a proof. This is just showing you that if it's going to be a quadratic relation, this is the only quadratic relation that can work. Just to make sure everybody's on the same page, does everyone agree with my algebra? Yes? All right, 12 over 24? For the people outside of math. I know the mathematicians can do fractions. 12 over 24? What's 12 over 24? I get 1/4. Who got 1/2? What department are you in?
Chemistry.
Chemistry. Oh, okay. Well, Did you have a lab incident? No. Let's check. 16 over 64, I cancel the 6's, I get 1 4. 19 over 95, I cancel 49 over 9. Now, this is a little bit more work because I get 4 8's and I have to work from there. But I do get 1/2 after the dust settles. So whenever you have, I don't know if you've seen this before, but whenever you have a 2-digit fraction with 2 digits in the numerator and the denominator, you can just cancel diagonally. And this is 3 cases. This is 3 times as much math as what we just did for Pythagoras. So by that argument, 12 over 24 is 1/4. This is why I use Excel to calculate grades. Okay. Just because you check something for a few cases does not mean you have proved it. But you can start to build intuition. So what I want to do now is I want to extend Pythagoras to a situation hopefully many of you have not seen. And a lot of this is joint conversations with Professor Garrity. There are advantages to having a building where offices are near each other and you can talk to people, just in case any architects are in the room. Anybody familiar with the Pythagorean formula on a sphere? Anybody familiar with a sphere? Nobody's familiar with a sphere. Okay, that's probably why we're playing Ultimate Frisbee. Alright, so you just spin the Frisbee, you get what's called a sphere. So a sphere, everybody has seen before. Have you ever thought of asking, is there a Pythagorean formula on the sphere? You should be asking stuff like this. When you see results, you should always be asking, how can I generalize? How can I extend? Where else might something like this be? I would claim that the reason I hadn't done this for a long time is I was taught mathematics almost by rote when I was young, and was not really trained to be creative in thinking, but really trained to regurgitate. It's taken a lot of years to get out of that, but when you see math, you always want to look at connections. So here is a sphere. I've zoomed in. Somewhere down here is the credit to where the image was drawn from. And I've drawn a triangle on a sphere. Do you think that there will be a relationship between the arc lengths? And if so, what would that relationship be? And again, I can take a right triangle. Should there be a relationship? Well, so here's spherical coordinates. Now, one of the nice things about giving a talk like this is we have mathematicians, physicists, chemists. I'm not sure if the other departments use spherical coordinates that much, and almost every division seems to have their own choice of spherical coordinates. I have either chosen what the physicists use or amalgamated what the physicists and mathematicians have done. Is this physics notation? Okay. I learned my notation in physics class before math class, so I do things like a physicist. So rho is the radius of my sphere, theta is the angle coming down from the North Pole, and then phi is how much you spin. Okay? So here are my spherical coordinates. What would the Pythagorean formula look like on a sphere? Now, one of the reasons we use radians is if you use radians, the length of an arc is basically the angle it sweeps out times the radius of the circle. Or a better way of looking at it is you look at the fraction of the total 2 pi radians of the circle that your angle fixes, and then you multiply that by the radius, and that gives you the arc length. So if I have a quarter of the circle, the circle's perimeter is 2 pi r. So I would then take the fraction of the angle I get, multiply by that, and I would have my length. This is one of the reasons why we like to use radians. So here are some facts we know. If A, B, and C are small relative to the radius r, I claim it should reduce to the regular Pythagorean formula. Imagine you have a sphere, I don't know, like the size of the Earth, and you draw a triangle of sides about 2 or 3 centimeters. You're not going to really notice the curvature of the Earth. And in this case, the Earth is going to locally look flat. And so whatever answer you have for the sphere, it should look a lot like the answer in the plane. So whatever my answer is, it should look a lot like the regular Pythagoras. Now, what happens when A, B, and C get large? Imagine the special case when you have an equilateral right triangle. So you have a triangle on a sphere with 270 degrees inside, where A, B, and C are all coming down in the same length. So obviously, as the sides get larger relative to R, strange things can happen. It seems reasonable to posit that the answer is only going to depend on the ratios of A over R, B over R, C over R. If I change from measuring things in meters to feet, it shouldn't really affect the functional form. So does anybody have any thought about what might come together with all these ingredients? What would you conjecture? Any thoughts? So Professor Gowdy and I took a long time to come to the following, and then in hindsight we should have hit it a lot earlier. Maybe a relation involving cosines, because the arc lengths are related to the angles, so maybe cosine should be reasonable. So a little basic algebra. Taylor says the cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial, da da da. If u is really small, then this is approximately 1 minus u squared over 2. So if I now take my three angles, if I assume r is large relative to a, b, and c, the cosine of a over r is about 1 minus 1/2 a squared over r squared. And if I just look at cosine of CR, cosine AR, and cosine BR, if I multiply the two on the right together, after all the algebra settles, I get c squared is a squared plus b squared minus 2a squared b squared over r squared. That looks a lot like the Pythagorean formula, and as r goes to infinity, this term becomes insignificant, it's going to reduce to Pythagoras. So, as a reasonable guess, maybe Pythagoras on the sphere is the cosine of c over r is the cosine of a over r, the cosine of b over r. And so I'm not going to go through the details of the proof. I will just pause. I'm recording this, I'll post this online. The slides will be on my webpage. Here's just running down the points in spherical coordinates, calculating what the length is. The proof basically just follows from the dot product relation. Of course, this then begs the question, how do you prove the dot product relation? So that you make sure you're not arguing in a circle or a sphere or whatever shape you want. So if I now write down Cartesian coordinates for the 3 points, one of the nice things, I can choose the first phi to be 0, the second phi to be pi halves. It makes the vectors particularly nice. The dot product is just r squared cosine theta A cosine theta b. You use the dot product formula. When the dust settles, there's spherical Pythagoras. So at this point, hopefully you've enjoyed what you've seen. You've seen proofs of the Pythagorean formula. You've seen how to generalize it. What should you be thinking next?
Where can I apply it?
Oh, okay, you're obviously not in math. No application, no. What else could you be thinking? So you've seen it on the plane, you've seen it in the sphere. 4 dimensions, and maybe more dimensions, or what other spaces. So keep generalizing. What's the next natural candidate? And I'm going to say that the next natural candidate is hyperbolic. So I don't want to go into what hyperbolic space is. We're running out of time. Can anybody tell me what the Pythagorean formula should be in hyperbolic space, even though I'm not even telling you what hyperbolic space is?
Replace cosine with cosh.
Replace cosine with cosh. Cosh of C is cosh of A and cosh of B, or cosh of the hyperbolic cosine. Absolutely correct. It generalizes exactly as you would expect it to. And so you want to see how far can you keep pushing this? What would it look like in other places? Can you get a sense of what the formula might be? If you have an idea of what the formula is, that is a great help in trying to prove it. So just quick conclusions. Math is not complete. There's always more to explore in conjecture. One of the things I hope you got out of this is that different proofs highlight different techniques, highlight different aspects of the problem. And I hope this gives you some sense of how we look at things. So thank you.